Welcome to this video on generators, power, and permutation groups. We will explore the fundamental concepts of abstract algebra and their applications. Our learning targets include understanding groups and generators, cyclic groups and orders, working with permutations, Cayley's theorem, and various applications. First, let's define a binary operation. A binary operator on a set S is a rule that combines any two elements of the set to produce another element of the same set. We can build up algebraic structures based on properties. Closure defines an algebraic structure. Adding the associative property forms a semigroup. Adding the identity element forms a monoid. Finally, adding the inverse property defines a group. If it is also commutative, it is an abelian group. A group is a set of elements combined with an operation that satisfies four fundamental properties. For a set G and a binary operation asterisk, G is a group if it satisfies closure, associativity, identity, and inverse properties. Groups can be finite, containing a finite number of elements, like Z4, under addition modulo 4. Alternatively, infinite groups, such as the set of integers Z under addition, have an infinite number of elements. The closure property means that for all elements A and B in the group G, the result of A asterisk B is also in G. The associative property states that for all elements A, B, and C in G, the order of operation does not matter. A asterisk B asterisk C equals A asterisk B asterisk C. The identity property requires an element quost quote cup E in G, such that for every A in G, A asterisk E equals E asterisk A equals A. The inverse property ensures that for each element quote 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 equals such that A asterisk A1 equals A equals E, the identity element. Here is a question. If an operation is associative, has an identity element, and every element has an inverse, what is necessarily true? The answer is that G is a group, as only the closure property is missing from the full definition, but is often implied by the context of a binary operation on a set. Another question: which of the following is not a group? Integers under multiplication are not a group, because most elements lack an inverse within the integers. Moving on to generators. A generator of a group is an element that can be used to produce every other element in the group using the group operation. A cyclic group is a group generated by a single element G. Every element in a cyclic group G can be written as a power of G. The element G is called a generator of the group. The order of an element A is the smallest positive integer n, such that A raised to the power of n equals the identity E. If no such integer exists, the element has infinite order. The order of a group is the total number of elements. By Lagrange's theorem, in a finite group, the order of every element divides the order of the group. Consider the group G equals I minus 1 dash I 1. The order of the group is 4. The order of each element, such as OI equals 4, divides the group order, confirming Lagrange's theorem. A permutation of a set S is a bijection from S to itself. Permutations can be represented using two-line notation, one-line notation, or cycle notation. Cycle notation shows how elements map in a loop. Disjoint cycles do not share any elements, which simplifies their representation and analysis. The symmetric group Sn is the set of all permutations of n elements with a size of n factorial. For example, S3 has 6 elements, including the identity, 3 transpositions, and 2 3-cycles. Cayley's theorem states that every group G is isomorphic to a subgroup of the symmetric group Sg. Simply put, any group element can be represented as a permutation of the group's own elements. For a group G, each element gauche A in G defines a function fa from G to G, where fa of x equals A asterisk x. Each of these functions is a permutation of the set G. As an example, for the group G equals 1 minus 1 under multiplication, the element 1 generates the identity permutation, 1 minus 1. The element minus 1 generates the swap permutation, 1 minus 1. Thus, the group of permutations for G is 1 minus 1, 1 minus 1. Group theory finds important applications in cryptography. It is the foundation for permutation-based ciphers and is used in block ciphers like DE for substitution and permutation steps, supporting key design and security. In combinatorics, Cayley's theorem links algebraic groups to permutations, which are vital for counting and symmetry problems. These concepts aid in algorithm optimization for searching and pattern recognition. To conclude, we have covered groups, generators, cyclic and permutation groups, and Cayley's theorem. These algebraic structures are crucial in cryptography for security and in combinatorics for pattern analysis. Thank you for watching this video.